I am H.S. Vishwanath, Selection Grade Lecturer from MEI Polytechnic. This is the session related to the design of RCC members, design of columns and footings. In this session, we are taking up the unit design of columns and footings. First, we will take up with the problems and also theory related to the columns, and then we will discuss the footings. Before moving towards the columns, let us see what do you mean by compression member. A compression member is a structural element which is subjected to axial compressive forces. This column is particularly it is the compression member. Compression member which is subjected to axial compressive forces. If members are subjected to axial compressive forces, that member is known as compression members. Compression members are most commonly encountered in reinforced concrete buildings, that is columns. Columns we are treated as in compression members which takes the axial compressive forces. How this compression member is classified? See, this compression member is classified into, in particularly related to the RCC, it is classified as in pedestal and columns. Columns, there are two types of columns, short columns, long columns. In this short columns and long columns, how we can define L by B? L by B, B is the side of the column. If L by B is 3 to 12, L is the length of the effective length of the column, and L by B is 3 to 12, then it is classified as a short columns. If L by B is between 12 to 60, then it is classified as long columns. And again these columns may be axially loaded plus uniaxial bending moment, axially loaded biaxial bending moment. This we will discuss in this session in detail. And also another classification of this compression member related to RCC is pedestal. If L by B is less than 3, effective length to least lateral size of the beam column is less than or equal to 3, then it is classified as a pedestal. Particularly in this topic, we are discussing about the columns and also that is short columns. As per the syllabus is concerned, we are going to design short columns only. What do you mean by column? Column is defined as a vertical compression member. Vertical compression member is called column. If it is a compression member is inclined, then it is called strut. Vertical compression member which mainly subjected to axial loads. If it is subjected to axial compressive load and effective length of which exceeds 3 times its least lateral dimension. That is what previous slide I have shown. If it is in more than 3 times least lateral dimension, effective length to least lateral dimension, then it is called as a column. That is, column is defined as a vertical compression member which is mainly subjected to axial load and effective length exceeds the 3 times of its least lateral dimension. This is the definition of column. Again, definition of pedestal is the compression member whose effective length is less than 3 times its lateral dimension is called pedestal. If you want to differentiate between the column and pedestal, it is related to the effective length to least lateral dimension. These are the few of the column sections which we are going to discuss in RCC. Column sections may be even T sections, I sections, but particularly related to our subject, we are designing the columns. This is square column, rectangular column, and then circular column. Okay, these three types of columns we are going to design in RCC. Even columns may be other different shapes according to the suitability of the site. How columns fails? You can observe here, this is the load acting. This load is acting compressive load. When compressive load acts, then columns fails by compression failure, that is crushing. You can observe here cracks on the column, or column may fail by the buckling. Buckling means it is a bending. Bending takes place along with the vertical axis. This buckling takes place normally in the long columns. Failure of columns due to buckling occurs in long columns, that is L by B or L by D is greater than 12, then columns fail by buckling. Whereas in short columns, usually columns fail by compression failure, that is crushing. And how we can define the strength of the column? Strength of the column depends upon the shape of the column, whether it is a rectangular, circular, square or I, T. Depending upon the shape of the column, strength of the column changes. And also size, what is the size of the column we are going to have, that also matters. And then cross section of the column, what is the B and D or diameter, that also affects the strength of the column. And one more important point is length, that is effective length. If length of the column changes, then load carrying capacity or strength of the column also varies. What is the function of the column? As how we can define this, if it is a column consists of a beam and slab, column with a beam and slab, then normally slab transfer load to the beam. First slab will transfer the load to beam, then beam transfer the load to column, finally column transfer the load to footing. This is the frame structure. If it is a frame structure consisting of an column, beam, slab, footings and all, then ultimately load will be taken by the column from beam and slab, then that load will be transferred to the footing. Footing in turn it will transfer to the soil. If it is an only slab and column is there, slab column section, then slab transfers the load to the column and then column transfer the load to footing. This is the system in the RCC frame structures. Mainly column is used to transfer the loads from beam and slab to the footing. Let us discuss the how mainly columns are classified. Classification based on the type of loading. There are the two types of loaded columns. One is axially loaded column, another is eccentrically loaded columns. In eccentrically loaded columns, there are two types, uniaxial bending and one more is biaxial bending. In this subject, we are going to design the axially loaded columns, and then in case of eccentrically loaded columns, uniaxially bending columns we are going to take up. Biaxial bending only concept will be discussed, because biaxial bending involves the huge amount of calculation that is beyond the scope of diploma level. Axially loaded columns. What do you mean by axially loaded columns? The columns which are subjected to loads acting along the longitudinal axis. If it is exactly at the centroid, if it is a centroid of the column load acts, then columns are classified as an axially loaded columns. See, axially loaded column is subjected to direct compressive stress only, no bending stress. Bending stress will not be there and bending moment will not be there, only compressive stress and direct compressive stress will be there on the column. Okay, you can see here, this is the column and this is the plan of the column. in the plan we can observe load is acting at center of gravity of this square section, exactly at center load is acting, and you can observe here load is, this is the elevation where P is acting exactly at the centroidal axis. There is no eccentricity in the column section due to load. This type of load is known as a axially loaded column. Okay, this column design is very easy compared to biaxial and uniaxial loaded columns. Then second classification is eccentrically loaded columns. In eccentrically loaded columns are those in which load do not act on the longitudinal axis of the column. This load will not exactly coincide with the center of gravity of the centroidal axis of the column. This type of situation is known as a eccentrically loaded columns. They are subjected to direct compressive stress and bending stress. It involves the bending stress as well as compressive stress. Therefore, moment we have to taken into account P into eccentricity. E is the distance from where P acts. Eccentrically loaded columns may be subjected to uniaxial bending, biaxial bending. As I already told you, uniaxial bending, biaxial bending. Two types of bending will take place. Here you can observe here, first one is this is figure B is eccentrically loaded column with uniaxial bending. What we can observe in plan, load is acting at a distance of E from the centroid. From the centroid along the x axis, it is acting at P distance. Okay, that is it is actually away from the centroidal axis. Okay, but it coincides the horizontal axis and vertical axis it is away. This type of situation, P will be acting away from the at a distance of E. Therefore, movement acts P into E. P into is the movement, additional movement acts on this column. This type of loading is known as a uniaxial bending. If it is an load is acting Ex and Ey at a distance of Ex from the centroidal axis, Yy axis, and Xx axis at a distance of Ey, then P is not coinciding with the horizontal as well as vertical axis, Xx and Yy axis. It is away from the Ey and Ex. Ex is the horizontal eccentricity and Ey is the vertical eccentricity. This type of situation where load acts away from both the centroidal axis is called as the biaxial bending. Okay, here we have to take the moment in both the directions. In first case, P into E is the one direction. Here P into Ey, P into Ex, Mux and Muy. Both moment we have to consider when designing the column. These are the examples. You can see cross section of the column where P is acting x axis as well as y axis. This is the uniaxially loaded column. It may be acts along the y axis away from E distance from xx axis, or P acting at a distance of E from the yy axis. These are the examples for the uniaxially loaded column. Practically, we can see practically if a column is provided on the site, which are all the axially loaded column, which are the axially uniaxial loaded, and which are all biaxial, we can identify. Here these are the column system in the frame structure at a distance of 4 meter, and here 5 meter is the distance. What we can observe, this A, column A is at center of these two axes. Therefore, load is acting exactly at the center. That is why A is classified as a axially loaded column. Whereas this column B is a uniaxial bending moment. It is a center is away from the yy axis. That is why these columns are B. Column B here also center is away from the y axis, here center is away from the x axis, B is away from the x axis. These columns are uniaxial bending moment, axially loaded with uniaxial bending moment columns. Whereas corner columns C is center is away from the x axis as well as y axis. That is why corner columns are biaxially loaded columns, that is axially loaded plus biaxial bending moment. Like this, practically when we are going to design the columns, depending upon the orientation and position about the x and y axis, we can classify columns into the three categories, that is whether it is axially loaded or eccentrically loaded columns. Next classification is classification of columns based on the slenderness ratio. This is also one of the important classification. We are going to classify the columns into short columns and long columns. In case of short columns, the columns is considered as a short column when the slenderness ratio of column, that is slenderness ratio means ratio of effective length to least lateral dimension. Here one more new word is least lateral dimension. Least lateral dimensions means size of the column which is least. For example, if it is a square column, size of the column is, if it is a 500 into 500, then least lateral dimensions will be 500 itself. If it is a rectangular column, if size is 300 by 500, then 300 is the least lateral dimension of the column. That is the least dimensions of the cross-sectional area of column is considered as a least lateral dimension. If it is an effective length to least lateral dimension is less than or equal to 12. If it is in less than or equal to 12, then it is classified as a short columns. If in case of long columns, slenderness ratio is a greater than 12, that is ratio of effective length to least lateral dimension is greater than 12, then it is classified as a long column. Simply what we can say, slenderness ratio is less than 12, it is short columns, slenderness ratio is greater than 12, it is a long column. Mathematically we can write effective length LEX or LEY divided by DRB. If it is a rectangular column, D and B are the size of the column, which is less than 12, then it is short column. If it is a greater than 12, long column. Here LEX and LEY are the effective length, not ordinary length. We have to take it as an effective length of the column, and D is the, D and B are the breadth and width of the column. Let us list the what is the difference between the short column and long column. That is what one is column is considered as in short when the ratio of effective length to its least lateral dimension is less than or equal to 12. Slenderness ratio is less than or equal to 12 is called as a short column. If it is a slenderness ratio is greater than 12 is called as a long column. And effective length of the column to its least radius of gyration. If it is the radius of gyration is less than to 40, then it is called the short column. If radius of gyration is greater than 40 is called as a long column. And one more important point is in short column buckling tendency is less, very low. It buckles least, whereas long columns easily buckles. Then load carrying capacity is high in case of a short column compared to the long column. And one more important point is the failure of short column is by crushing, whereas failure of column is generally buckling in case of a long columns. This is the major difference between the short column and long column. Next we are as mentioned previous sessions, previous slide, that is effective length, which is the very important we have to consider as per the IS 456-2000. What do you mean by effective length? The unsupported length of the column is the clear length or height between the floor and lower length of the ceiling. One is unsupported length. Unsupported length is clear height of the column, that is from the floor to the floor to the ceiling bottom is the unsupported length, whereas effective length is the part which takes under the buckling. Column will not buckle completely, some part will buckles depending upon the end conditions. If whether both ends are fixed or both ends are hinged or one end is fixed and other end free, depending upon the end conditions, this part of the column will buckles. That buckling position we can if we measure, that is known as a effective length of the column. But measuring an buckling length or effective length is very difficult. That is why IS 456 and 2000 has given few guidelines and tables to calculate the effective length of the column. I have taken a few tables from the IS 456 for which we are going to calculate in our problems. Four important major conditions I have considered here. One is see, according to IS 456 table, to calculate effective length, effectively held in position and restrained against rotation at both ends. This is the one technical term you should understand clearly. Effectively held in position and restrained against rotation. That is, column is completely fixed. Effectively held in position means it is one position, it is not moved from one place to another place, and also it will not rotate. When it is not allowed to rotate and it will not move one place to another place, then it is called as an fixed. Both ends are fixed. Okay, there is no rotation takes place at this point as well as bottom. Top and bottom, both the places, if it is no rotation takes place as well as it is held in position, then that condition is known as a both ends are fixed. Okay, in problems they will not mention both ends are fixed. They will give this condition, effectively held in position and restrained against rotation at both ends. Then you should understand it is the both ends are fixed. When both ends are fixed, if you want to calculate the effective length, it will be 0.5 L. L is the unsupported length. Unsupported length means it is the distance from the ceiling to the bottom of the floor. That is multiplied by 0.5, you will get the effective length of the column. Second condition is effectively held in position at both ends. Held in position means it is fixed at the both ends. Restrained against rotation at one end. One end is pinned. Pinned means hinged. Hinged. Therefore, it can rotate. But one end is fixed, completely fixed. No rotation is allowed. Another end is hinged. When it is hinged, there will be rotation will take place. Just like a door. If your door is having a hinge, you can rotate it, rotate the door, but you cannot displace the door from the point. That is one point it is fixed, but there will be rotation. Whereas if you take some fixed window, fixed glass to the window, there is no rotation as well as no, it will be fixed also, and there will no rotation takes place. This type of condition is called as a fixed at one end and hinged at the other end. When this condition is given in the problem, then you refer the IS 456 table and multiply with the 0.7 L. You get the value from the IS 456. Then for given unsupported length, you have to multiply with 0.7. You will get the effective length of the column. L is the unsupported length of column. And third condition is effectively held in position at both ends, but not restrained against the rotation. Here you can see both ends are hinged. Both end it will allow the rotation. This type of condition, if you want to calculate the effective length will be equal to the unsupported length, because both ends are hinged. Complete column will bends. It will buckles, complete column will buckles, therefore complete part of the column will acts in the buckling. That is why length will be, unsupported length will be equal to the effective length. Fourth condition is effectively held in position and restrained against rotation at one end, but not held in position. Held in position means it is not fixed also and not restrained. It is rotation also allowed and it is not fixed, it is free at the one end and fixed at the other end. Okay, this is just like a light pole or a flag hoisting pole. You can see one end is fixed, another end is completely free. This type of situations, if you want to calculate the effective length, that will be equal to 2 into L. L is the unsupported length. Whatever the length is given, multiply by 2, you will get the effective length of the column. These are tables available in IS 456 2000. You have to refer IS 456, which is allowed in the examination, and note down the values of a coefficient and calculate the effective length. And then let us see how reinforcement is provided in the column. RCC columns are provided with the two types of reinforcements. Two important reinforcements are provided. One is longitudinal reinforcement, another is transverse reinforcement. What do you mean by longitudinal reinforcement? See, you can see here I have given the figure in which you can observe which is longitudinal reinforcement, which is the transverse reinforcement. Transverse reinforcement, you should tell always lateral ties, not stirrups. It is a ring which is called as in lateral ties. Rings are called the lateral ties, and vertical bars are called the longitudinal reinforcement. Longitudinal reinforcement is the main reinforcement which will check the compressive force. Okay, this is the column with the lateral ties. Sometimes circular columns will be provided with the, instead of rings, it will provided with the like this type of spiral or helical ties. Instead of lateral ties, there may be provision of spiral ties for the circular columns. Okay, these are the reinforcement provided for the columns, and distance between the one tie to another tie is called the pitch. Spacing between the one tie to center distance is called the pitch. Okay, in plan you can see 4 bars are provided, longitudinal reinforcement, and lateral ties are provided. Here you can observe here in circular column 6 bars or longitudinal bars are provided, and then spiral ties are provided. This is the site in which we can observe how column is tied to the footing with the lateral ties, vertical longitudinal reinforcement as well as the lateral ties, and also bottom it is bent L shape, it is extended 300 mm into the footing to distribute the load. This is the bottom of the column, bottom portion of the column, where longitudinal reinforcement is bent in all the directions and which is tied to the footing. This is the reinforcement tying in field. You can observe these are the longitudinal bars, and these are the lateral ties which is tied to the longitudinal bars. After tying at the side, then they will erect in the field actual position, center it according to depending upon the grid how they are marked. This is the cages. Like this, if it is in n number of columns, all the columns will be tied in the one place, and then they will transport to the field. One yard, they will prepare the yard where reinforcement tying will be takes place. Afterwards, it will transfer to the site, and they will erect according to the grid given in the grid or column marking is given in the drawing. This is the circular column. You can see in circular column rings are provided. This is a circular rings are provided which is called as in lateral ties. This vertical rod is the longitudinal reinforcement which is tied to the footing. This is one more sketch figure you can see. This is the column, circular column, fabricated, ready for the installation. And this is the one huge circular column with the massive reinforcement you can observe. with the ties as well as longitudinal reinforcement. And this is the spiral ties. You can observe here spiral ties, how we can provide for the circular column. It is just like a spiral rotating. Okay, this is the one of the lateral ties normally provided for the circular columns. This is the bunch of rings how bar bender will prepare, and then they will insert in the longitudinal bars and they will tie up. This is the one view where you can observe this how lateral tie is tied to the longitudinal reinforcement. Okay, this is the one where junction of the tie. Okay, then it is tied to the longitudinal bars. This is the column and beam structure, frame structure. Usually you will see everywhere frame structure before bricks and all infills are filled. Structure will be looks like this. It is completely consists of an columns. This is the column, and then beam slab system. This entire structure will transfer the load to the columns, and this column will transfer the load to the footings. Okay, this is the most popular structure what we can see in India, frame structure. That is why columns are very important major role, even resisting the earthquake also. This frame structure is very important to design for seismic zones as well as entire loading system. Even if we place the infills columns, even brickwork and all the load will be transferred to the column. This column will transfer the load to the footing. Okay, let us see what are the codal provisions given in the for the reinforcement, minimum reinforcement, how much minimum reinforcement we have to provide, and what is the maximum reinforcement as per the IS 456. We should follow IS 456 properly for designing the columns. Minimum area of reinforcement. A minimum area of reinforcement should be always provided in the column to resist the tensile stresses which may be caused due to eccentricity of the loads. As per the code, whatever the provision is given, that minimum reinforcement should be provided. Even load is very small. First, one more is longitudinal reinforcement is also called as a main reinforcement. What is the purpose of longitudinal reinforcement? First, we will see to share the compressive load along with the concrete, thus reducing the overall size of the column and leaving more space for utilization. Okay, if it is in reinforcement is provided properly, we can reduce the size of the columns. If longitudinal reinforcement is designed properly, size of the column will be reduces. Once size of the column is reduced, then we can use the maximum space. That is the one point. And then to resist the tensile stresses developed due to any movement or accidental eccentricity. If it is in any eccentricity occurs, then movement will be there. That movement will create some tensile stresses in the column. That will be resisted by the longitudinal reinforcement. To impart ductility to column. This ductility is very important in case of seismic zones and earthquake resistant structures. It will give the ductility to column. Then to reduce the effect of creep and shrinkage are the one of the major problems in the concrete structures what you have studied in the first semester concrete technology. That is will reduced by this longitudinal reinforcement. As per IS 456, the longitudinal reinforcement should not be less than 0.8% and it should not be more than, maximum also given 6%, minimum 0.8% and maximum 6% of the gross cross-sectional area of the column. 0.8% into area of the column. If you multiply, whatever the area we will get, that is the minimum steel you have to provide, and 6% of the cross-sectional area for the column. that is 6% of the area of the column is the maximum limit. We cannot provide more than 6%. If it is a more than 6%, entire column will be consists of in steel only. There is no place to provide the concrete. And one more point is observed in the IS 456 due to practical difficulty in placing and compacting the concrete. Because if it is a steel is large or huge, then it is very difficult to compact the concrete and allow the concrete aggregates inside the column. Okay, that is why it is restricted 4%. When we are designing the columns, it is better to restrict the column percentage of steel up to 4%. If it is an unavoidable circumstances and huge load, then only we can go for the 6% steel. Normally, we will provide the steel between the 0.8% to 4%. And then what is the purpose of transverse reinforcement? The transverse reinforcement is provided along the lateral direction. Lateral directions means perpendicular to the column axis, that is rings. Lateral directions of the column in the form of a ties or spirals enclosing the main steel. What I have shown in previous slides, that sketch how we are providing the lateral ties. That way we have to provide the transverse reinforcement according to the IS 456. The purpose of providing transverse reinforcement. What is the purpose of providing transverse reinforcement? One is to hold the longitudinal bars in position. First important point is whatever the longitudinal bars are there, it will spread. If it is in rings are not provided, lateral ties are provided. To hold the longitudinal bars in position, we need the lateral. That is, we have to provide the cover. We have to maintain the cover between the longitudinal reinforcement and the shuttering. Whatever the column form work what we are providing, we need the space. That provision of cover can be possible after providing the lateral ties. And then to prevent the buckling of main longitudinal bars, to prevent the buckling, we need the transverse reinforcement. To resist diagonal tension caused due to transverse shear developed because of any movement. If any movement, any cracks is developed, that cracks will be avoided by this transverse reinforcement, just like a shear reinforcement. To impart again one more important, ductility to column, to resist the forces due to the fatigue or impact loads and also seismic loads. It will give the ductility. To prevent the longitudinal splitting or bulging of the concrete, confining concrete, it will confine the concrete within the size. Okay, it will avoid the bulging of the concrete. Therefore, strength of the column will be increases. These are the few of the points which is we have to keep in mind due to which transverse reinforcement must be designed. Next one more important point is number and diameter of the longitudinal reinforcement. How many bars we have to provide as in longitudinal reinforcement, vertical reinforcement? 4 in rectangular column as per the IS 456-2000. For rectangular column or square column, we have to provide minimum 4 number of bars, not 2. We cannot provide 1 bar and 2 bar in the column. Minimum 4 we have to provide. And then minimum 6. We have to provide minimum 6 bars in the circular column, not 4 bars. Even if it is in 5 bars or you have got the design 5 bars, you have to round it to the 6, not by 4 or 5. And even in rectangular column design or square column, if you get 3 bars or 2 bars, you have to make it as in 4 bars. It should be minimum 4 bars. At each corner 1 bar should be provided. The bars shall not be less than 12 mm in dia. One more important point is minimum diameter of the bar what you are going to assume should be 12 mm bar. It should not be less than 12 mm dia of bars for the longitudinal reinforcement according to IS 456-2000. And then for lateral ties, what is the spacing? Spacing of the lateral ties. This also given in the IS 456 code. Pitch spacing between the one ring to the another, that should be the pitch of the transverse reinforcement should not more than the least of the following. Following three conditions has been given. The least lateral dimension of the column. One is least lateral dimension of the column. Size of the column which is least, that we have to consider. Second one is 16 times the smallest diameter of the longitudinal bar. Whatever the diameter of the bars provided in the column, longitudinal bars, for example say 20 mm dia bar is provided, then 20 into 16 times we have to multiply. Third one is 300 mm. Out of these all three, maximum spacing should be 300, it should not be greater than 300 mm. Okay, these are the three conditions given in the code. You have to calculate all the three conditions, out of which is the least, that you have to provide. For example, least lateral dimension of the column is 400, and 16 times diameter, if you get around 500, and 300 is the least. Out of three conditions, you have to select as in 300 mm center to center. All the three conditions we have to calculate, and out of which least should be considered for the spacing. Then diameter. Diameter of the lateral ties shall not be less than 1/4 diameter of longitudinal bar. Whatever the bars are provided in the reinforcement, longitudinal bars, that divided by 4 you have to calculate, and then 6 mm. In these two, whichever is more, that we have to consider. For example, if it is in 20 mm dia bars are used, 20 divided by 4, that will be equal to 5 mm, and one more is 6 mm, out of which maximum is 6 mm. We have to provide the 6 mm dia bars. Like this, we have to calculate and find out what is the diameter of the lateral ties. And then one more important point to be considered while designing the columns is minimum eccentricity. Because column cannot be always axially loaded. Axially loaded means exactly centroid of the column we cannot apply the load. Some eccentricity always be there due to non-homogeneity of materials and imperfections in construction. Construction is not proper, or alignment is not proper. Due to this type of situations, normally there will be some eccentricities will be there, that due to that eccentricity there will be movement. Okay, that is why code allows minimum eccentricity as per IS 456 class 25.4, which recommends columns should be designed for minimum eccentricity given by E minimum is equal to L by 500 plus D by 30. If you see IS 456 class 25.4, you can get this formula, E minimum is equal to L by 500 plus D by 30, or it should not be more than 20 mm. If it is more than 20 mm, definitely you have to design the column as an eccentrically loaded column. Okay, within the 20 mm, you can design column as an axially loaded column. Here L is the unsupported length, you should not take the effective length, it should be unsupported length, that is floor to ceiling height, and D is the least lateral dimension of the column in the direction under the consideration. And also as per code, E minimum should be less than or equal to 0.05 D. This we will take up when we are solving the problems. And one more important point is cover to reinforcement. Normally for the nominal cover as per the IS 456, following are the 2 points you have to consider. It should be 40 mm, and second is the diameter of the bar. In case of small size column, minimum dimension 200 mm, you should know, column size should not be less than 200 mm. Okay, minimum size 200 mm, or where very small column size 200 mm is provided, then we can go for the cover 25 mm. Otherwise 40 mm cover should be provided for the columns. And for design purpose, we have to see how much load column will take. To know the load, one formula is given in the IS 456 class 39.3, factored or ultimate axial load. How to calculate the factored load? Factored load PU is equal to 0. This is the very important formula which is required for the calculation purpose. When we are designing, often we use this formula. Pu is equal to 0.4 FCK AC plus 0.67 Fi ASC. 0.4 FCK AC, you should know all these terms. FCK is the characteristic strength of the concrete. If it is a M20 concrete, 20 newtons per mm square, M25 concrete, 25 newtons per mm square. And then AC. AC is the area of the concrete. Area of the concrete. Area of the concrete means whatever the gross area means size of the column minus area of the steel. If you minus the area of the steel, you will get the area of the concrete. ASC is the longitudinal reinforcement. Longitudinal reinforcement is the main reinforcement. ASC is the longitudinal reinforcement. Longitudinal reinforcement into Fi. Fi is the yield strength of the steel. If it is an Fe 415 steel, 415 newtons per mm square. Fe 500 steel, 500 newtons per mm square. Fe 250, 250 newtons per mm square. This 0.4 FCK into AC plus 0.67 Fi into ASC, you will get the factored axial load. Axial load is equal to factored axial load divided by 1.5, because factored load will be always multiplied with a 1.5 working load. Column members are to be designed for a minimum eccentricity of the load in two perpendicular directions. First we have to check minimum eccentricity, and then column should be designed. That minimum eccentricity, previous slide what is given formula, this by using this formula you have to calculate the minimum eccentricity and then check whether it is within the prescribed limit. If it is within the limit, then only we can go for this formula. Factored axial load Pu is equal to 0.4 FCK AC plus 0.67 Fi AC. You should note down that this formula is available in IS 456 2000 class 39.3. This class is very important, and also this minimum eccentricity, which is the class IS 456 class 25.4, where you will get this minimum eccentricity. And then finally what we will see, assumptions made for the limit state of collapse in compression member. This is also given in the IS 456 2000. What are the assumptions what made for designing the compression member? In compression member, plane section normally to the axis remains plane after bending. One is plane section always remains plane after bending, that is neutral axis remains plane after bending as well as the before bending. That is the one important assumptions made in the design of a compression member. Second one is the relationship between stress strain distribution in concrete is assumed to be parabolic. Whatever the relationship between the stress strain distribution is assumed as a parabolic. That is, the maximum compressive stress is equal to 0.67 FCK divided by 1.5. If you divide 0.67 FCK divided by 1.5, you will get 0.446. This is the maximum compressive stress developed in the column. This is the one more important assumption made in the design of a compression member. Third assumption is the tensile strength of the concrete is ignored. We are not considering the tensile strength of the concrete, because here whatever the formula here shown, it is the axial compressive force load taken. Axial compressive load taken by the column. Pu is equal to 0.4 FCK AC plus 0.67 Fi ASC. Here ASC is the area of compression reinforcement. We are calculating the compression reinforcement only, not AST. Area of tensile reinforcement is not at all provided here. Only compression reinforcement is provided. That compression reinforcement is in the form of a longitudinal reinforcement. this longitudinal reinforcement will take the compressive force directly. Okay, that is why we are not considering the tensile strength of the concrete. Therefore, the tensile strength of the concrete is ignored. This is the third assumption made in the design of a compression member. Then fourth assumption, the stresses in the reinforcement are derived from the representative stress strain curve for the type of the steel used. Stress strain curve is given in the IS 456. Whatever the representatives shown in the stress strain curve, that stresses in the reinforcement are derived from that representative curve. Okay, this is the one more very important assumption made in the design of a compression member. The maximum compressive strain in the concrete in the axial compression is taken as a 0.002. The maximum compressive strain in the concrete in the axial compression is taken as a 0.002. This is the maximum compressive strain taken, and then the maximum compressive strain at highly compressed extreme fiber in the concrete subjected to the axial compression and bending when part of the section in tension is taken as a 0.0035. This is the 0.0035 is the maximum compressive strain considered in the extreme fiber. Okay, and then axial compression it is taken as an 0.002. These are the major assumptions made in the design of a compression member as per IS 456 2000. Okay, these are the basics what we discussed in this session related to the design of a columns. What we are understood in this session is one is what do you mean by compression member, and which is the major compression member we are considered in the design of columns, the design of the RCC members, that is column. Okay, in column we are classified into the two categories. One is short column and long column depending upon the slenderness ratio, and another classification depending upon the position of the load, that is axially loaded column and uniaxial biaxially loaded columns. Like this we are divided the columns depending upon the loading and depending upon the slenderness ratio. After knowing the classification of the columns, how column reinforcement is provided, there are the two types of reinforcements are there, longitudinal reinforcement and lateral ties. What is the maximum permissible limit and minimum permissible limit for the longitudinal reinforcement, and how pitch is calculated for the lateral ties, and how to decide the diameter of the lateral ties, and how to decide the diameter of the longitudinal reinforcement. Everything we discussed in this session, and which is according to the IS 456. And also we have observed there is a minimum eccentricity given, provision is given in the our code, and also how to calculate the PU, that is axial load, and also what that formula where it is available, that also we observed. And finally we discussed about the assumptions made in the compression demonstrate of design for compression members. Okay, fine, thank you. We will meet in next session.